Hi everyone, my name is Pushu. Today, I want to take you on a journey, not a journey around the world, but a microscopic journey inside our own bodies. We all know that for the people with lactose intolerance, this little pill lactate is a lifesaver. But have you ever wondered about the incredible challenge this pill faces? It's an enzyme, a protein. As we learned in the biology class, proteins are fragile, right? So, how does this pill survive in the harsh, acidic environment of our stomach to do its job in the intestine? Today, I'm presenting the survival guide of a lactate pill from stomach to intestine. Here's our roadmap for today. First, we will look at the background theory regarding enzymes and pH. Then, we'll dive into our lab 4 simulation, where we mimic the environment of the small intestine. Third, I will pose a stomach hypothesis. What would happen if we tested an enzyme in stomach acid? Finally, I'll connect this back to the real-world environment to review the engineering solution that solves the biological paradox. Let's start with the biology. We know that from lecture 16 that enzymes are extremely sensitive to the environment, especially for pH. Please look at the graph on the left. This is a classic example comparing pepsin and trypsin. Pepsin, or the black line, loves acid. It works best in the stomach at pH 2. Trypsin works in the intestine and survives at a neutral pH around 8. Our hero today, lactase, functions in the small intestine, which has a pH around 7.4. This suggests that lactase should behave more like trypsin. If it encounters a pH of 2, like in the stomach, series predicts that it should denature and lose all the activity. So how do we test the lactase activity in our lab? In the lab 4, we designed a specific reaction system. First, for the mechanism, we could not use actual lactose because its products are colorless. Instead, we use a clever mimic called OMPG. As you can see in the diagram, which when lactase causes OMPG, it releases own nitrophenol, which is yellow color. This allows us to visibly check and track the reaction. Secondly, the conditions. This is the most critical part. We use PBS buffer. Does anyone recall the pH of PBS buffer? It's around 7.4, right? By using PBS at 37 degrees, we were effectively simulating the optimal solutions of human small intestine. Now, let's look at our results from the intestine simulation. The graph shows the absorbance of our reaction over 2 minutes. The x-axis is time, then the y-axis is absorbance, representing the product concentration. As you can see that we got a beautiful positive linear slope. The R-square value is 0.865, which indicates a strong linear relationship. The data tell us a clear story. In an environment like the small intestine, the lactase enzyme is highly active and stable. It works exactly as intended. But as scientists, we must ask the question, can we choose to trust the data? To ensure the reliability, we perform 3 technical replicates for every single time point. The arrow bars you see here represent the standard deviation. You might notice the arrow bars are a little bit larger in the middle groups. This variability likely comes from human factors, like some slight delays in pipettes in the stop solutions. However, even with this noise, the overall trend is undeniable, right? The signal at 120 seconds is significantly higher than 30 seconds. This confirms us that our finding of high enzyme activity at pH around 7.4 is robust and reproducible. To part 3. So we have proven the enzyme works in the intestine, but here's the challenge. It has to pass through the stomach first, right? I propose a theoretical extension to our experiments. The stomach challenge. Current model on the left. That's what we did. The PBS buffer and pH 7.4. The result is a yellow active solution. And I propose a model on the right. What if we kept everything the same temperature, same substrate, but we swapped the buffer for simulated gastric fluid at pH 2? Based on our background theory, we hypothesize that the high concentration of hydrogen ions will disrupt the enzyme structure, leading to denature. The result would be a clear colorless tube on the right. If we were to plot the hypothesis, it would look at this graph. The green solid line is our actual data from lab 4, high activity at pH 7.4. The red dashed line is our prediction for stomach, a flat line near 0. This creates a paradox. If the enzyme dies at pH 2, how does the pill we swallow ever work? It should be destroyed before it ever reaches the intestine. The answer to the paradox lies in pharmaceutical engineering. Please look at the diagram on the left. For stage 1, in the stomach, the pill is coated with special enteric coating. This polymer is acid resistant. It acts like a shield, keeping the enzyme safe inside. Stage 2, once it hits a neutral pH of 7.4, the coating dissolves, releasing the active enzyme. Stage 3 is our lab. This brings us back to the crucial detail in our procedure. Remember the step 1? We crush the tablets. Why? By crushing it, we mechanically can bypass the coating, simulating the related state of enzyme in the intestine. This allows us to measure its activity directly. To summarize our findings, what we have proved, our lab data confirm that lactase is indeed highly effective at pH 7.4. Biological theory tells us that it cannot survive in the stomach pH 2. The pill uses an enteric coating to bridge the gap. Last, the inside, our experimental step of crushing the pill was actually like a simulation of the coating dissolving. So to wrap up our journey, we started with a contradiction, a protein that needs to work in the intestine but must survive the acid. We use data to verify its potential in the right environment. And we identify the hidden hero, the entire coding that makes this possible. A critical reflection could be, If we wanted to fully validate the drug design in the future, we could run a new experiment, placing a whole uncrushed tablet in Th2 acid. If this design is good, we could see zero activity, not because the enzyme is dead, but because the shield is holding. Thank you. And finally, thank you for your listening. Thanks for Professor Joohyun Lee and the lab instructors, and also my classmates. Here's the last references for my slides. Basically, come from the lab 4 and the lecture 16. That's all. Thank you.